Welcome back to Course 212. In this lecture, we are going to start with Chapter 6 of the prescribed textbook, which deals with trees. Trees are a data structure that you will spend a lot of your time with. We will discuss all kinds of variants, and hopefully by the end of the semester, you will really learn to appreciate the efficiency of this approach to storing data. Alright, so far we have only dealt with linear data structures. Specifically, you by now have a lot of experience with arrays, dynamic arrays, and linked lists. Linked lists have some benefits compared to arrays. For example, inserting elements and deleting elements from a linked list is more efficient than inserting or deleting from an array because you do not have to shift the elements around. On the other hand, this benefit comes with a price because now that insertion and deletion are efficient, the search or random access is kind of suffering unless you create something more complex such as a skip list. But by default, linked lists basically have a single point of entry, right, which is the head or the tail. And because there is no random access, you can't just go straight to the middle of the linked list. You would typically spend quite a bit of time looking for the specific element that you are trying to access. So trees were basically invented to try and mitigate this. Another thing that doesn't really get captured by a linear data structure is the potential hierarchical relationships between the elements. In other words, what if some elements in your data structure are actually more important than others? Perhaps if it's customers, maybe some customers you want to prioritize and maybe process the query fast. So let's say if a pensioner joins the queue, you want to push him to the front of the queue or something like that. So if there are relationships between elements, if not all elements are equally important, then perhaps you also want to capture this hierarchical structure in your data storage structure. That is exactly, once again, what trees capture very, very nicely. So why trees? Short answer is they are hierarchical by design, and also they are efficiently searchable. All right, so let's jump into it and see what trees are all about. First of all, let's try and get some terminology out of the way. So what you're looking at is a data structure that we typically refer to as a tree. A tree has an entry point just like a linked list. With the linked list, we usually speak of the head of the list. With the tree, just because we're now going with this biological metaphor, we are going to refer to the head of the tree as the root of the tree. So you can think of the tree as like this upside down tree, right? We have the root, which is right on top, and then the branches go from the roots to the bottom. We have nodes in the tree, so every single element of the tree we will refer to as stored inside of a node of the tree. Nodes can be terminal or non-terminal. A non-terminal node is a node that is somewhere along the path, but not at the very, very bottom of the tree. But if you follow some path from the roots and you reach the end of a particular branch, that node would be referred to as a terminal node. And another word for it is the leaf of the tree. So again, think of this as a tree that has been flipped upside down. The root is at the top and all the leaves are at the bottom. And then the connections between the individual nodes are referred to as the arcs of the tree. Another very important thing, I already told you that trees aim to capture potential hierarchical relationship between elements. So an element stored at the root might be more important than the element stored in the leaves of the tree. And because this potential hierarchical relationship is inherently present in the structure itself, there is something very important that we can refer to if any two nodes are considered. Any two adjacent nodes can be classified as the parent and the child. So two adjacent nodes are the nodes that are actually connected by an arc. If two nodes are connected by an arc, then we will say that the node above is the parent and the node below is the child. So if you look at the root is the parent of these three nodes. And between these two, for example, the one that's closer to the root as the parent, the one that below is the child. Between these two, the leaf would be the child, and the node just before the leaf would be the parent of this leaf. So the parent-child relationship is important just because I will refer to a parent and a child quite a lot. So just make sure the terminology makes sense to you. All right, so you have seen a tree, and just going back to this picture, I think I just want to give you an intuition before we jump into code and traversals and algorithms that can be applied to this data structure. I think the easiest way to think of a tree is to think of it as of a linked list that basically branches out in multiple directions, right? So you already know how to code a chain of nodes. Every single node can have a pointer to the next node, and you can have this nice chain that algorithms can be applied to. Now, a tree is basically also a collection of these chains that are all sort of interconnected. The only real difference between a tree and a linked list is that a single node will actually have multiple next pointers, right? Multiple chains can originate from a single node. You also know what recursion is, so it might help if I tell you that trees are defined recursively. We will say that a tree with no nodes at all, an empty structure basically, is an empty tree. And then if you have k disjoint trees, and then you create a node which is a parent of all of these trees, then that resultant structure is also a tree. In other words, let's say you have two disjoint trees, the yellow tree here of just two nodes and the blue tree here with three nodes. If I now connect the two by defining a node which is a root to both of these nodes, then the resultant structure is also a tree. So combining any two trees by a root at the top makes a tree. What is also important is, just like in a real tree, the branches, every single branch is a unique path. You can't have multiple paths through the tree that take you to the very same leaf. So in this example, the structure on the left is a valid tree because to every single leaf, there is only one unique path that you can take. The structure on the right is not actually a valid tree because to this leaf in the middle, you can either go through the left or through the right-hand side of the tree. So the fact that there are two paths leading to the same output, that actually makes this not a valid tree anymore. So the paths through the tree to the leaves should always be unique. In fact, the structure on the right-hand side also has a place. If the uniqueness of the paths is not preserved, a structure like this would be referred to as a graph, and we are going to come back to this, I think, in chapter 8. So stay tuned, sometime later in the semester, we will talk about more complex structures, which are also variations of the same thing. But for now, let's assume the uniqueness of the path. It's an important property of trees. Some more terminology, just because we are starting out and it's important to get this straight. If we speak of a length of the path, we basically refer to the number of arcs taken from node A to node Z. So in this example, the length of the path from A to B is just 1 because only one arc is taken. The path from A to E, on the other hand, is 2 because you have to make 2 hops. You have to follow 2 arcs to get from A to E. Every single node in the tree has a level, and the level of the node is basically the length from the root to that node plus 1. Why the plus 1? Well, because we want to treat the root as a node at level 1, because there are no arcs that you take. You take 0 arcs to get to root. Root is your starting point. 0 plus 1 will give you the 1, so the level of A is 1. On the other hand, to get to E, for example, you have to take 2 hops. You travel down 2 arcs, but its level is 3 because 2 plus 1 gives you 3, and logically it also makes sense if you think of the tree as the nodes sitting on different levels. This would be my level 1, level 2, and level 3. So D, E, and F are all sitting on level 3 of the tree. We also say that a tree has a height, and height is basically the length of the longest path in the tree, right? It's the maximum level of the tree. In this particular case, the longest branches are 2 arcs long, so the level of D, E, and F is 3. 3 is as deep a level as you can go, therefore we'll say that the height of this tree is 3. On the other hand, if I added another node, maybe just connected to E, and left D and F as is, that would have still increased the height of my tree, because the longest branch would now have been 1 node longer. Okay, so that is all good and well. Hopefully this makes sense. Trees are branched out linked lists, and we apply a bit of the tree terminology. Instead of talking of the head, we will talk of the root. Instead of speaking of the tail, we now have multiple tails, and the tails are basically the leaves of the tree. Let's see how the structure can actually be made into an efficiently searchable structure. Well, we haven't really discussed how exactly data is going to be distributed through the tree. So let's just take some attempt at taking a linked list and storing linked list data in a tree-like structure instead. So here's a comparison. This is a picture directly out of the textbook. I have the following linked list, which stores 1, 2, 3, 4, 5, 6, 7, 8 elements. I want to store these 8 elements in a tree instead, just to see if that is actually going to give me any benefits in terms of access speed. Well, because we haven't really decided on how we're going to store the data in the tree, let's just say we choose a tree where every single node can have a maximum of 3 children, and then we will just start filling it in from the top. So the first element in the linked list is 2, so 2 becomes the root, then 10, 12, and 13 I inserted into the tree as the children of 2. Then 20, 25, and 29 I inserted into the next level of the tree, because we obviously ran out of space in level 2. So 10 will have then 3 children, 20, 25, and 29. Because 10 has run out of space, we are only allowed to have 3 children per node. 31 will become the child of 12. Alright, so we have managed to take the data and transfer it into the tree. Would this necessarily be more efficient to search? Well, let's say we are just accessing specific values. To access 25 in the linked list, we have to make 1, 2, 3, 4, 5 hops, and in 5 iterations we're going to get to 25. With the tree, on the other hand, because we now have multiple branches, the length of individual branches are shorter than the length of the entire linked list. In fact, we will never make as many as 5 hops, because the depth of the tree is only 3 levels, so the maximum number of accesses that we're going to make is 3, right? Especially if we know which branch to choose. So to get to 25, we only need to make 2 hops, which obviously is faster than making 5 hops. Let's try to access 12. Again, in the linked list it takes 2 hops, in the tree it only takes 1 hop, so it seems like this idea might be worthwhile. It seems like distributing the way you store elements in your linked list, it seems that branching out might actually be a good idea. However, one question remains unanswered here. In my comparison, I sort of assumed that I would know that 25 was stored here in the leftmost branch of 2 and in the middle branch of 10. But how exactly would I know that, right? Or to go to 12, would I really know that I should follow the middle path, or will I first waste my time and search the left path before I actually go to the middle, right? So for this to be efficiently searchable, I need to define somehow some criteria that will allow me to know exactly which branch to follow to find a specific element. And that is where binary search trees come in. Before we discuss binary search trees, let's just discuss binary trees at large. You are computer scientists or computer engineers, so you guys know what binary stands for, right? And obviously, as the name suggests, binary is something that works with powers of 2. So a binary tree is a special kind of tree where every single node is allowed to have a maximum of 2 children. Not 3 like on the previous example, but only 2. And because there are only 2 children max, we will also refer to these children not as child 1 and child 2, but rather as the left child and the right child. Let's quickly look at some examples. All of these are valid binary trees. The red guy here has no children at all. This gray guy here on the right hand side, we have a root that only has 1 child, and that child is on the right hand side, so we refer to it as the right child. Here is a yellow tree. It's also a binary tree because not a single node has more than 2 children. Root has a single child, which is a right child, and then the child of roots is also a parent to 2 more leaves, 2 more nodes. It has a left as well as a right child. This green tree only has a left child, and this blue tree is the biggest of them all. The root has 2 children, left and right, and its left child also has a left child of its own, and the right child is a parent to a left as well as a right child. Okay, so these are binary trees. They are more restrictive than the tree on the previous slide. You're only allowed to have 2 children per node. Just a little bit of math, because these trees are binary, it actually is quite easy to figure out exactly how many leaves would be on every single level, because as you can see, if the tree is fully filled on every single level, then the number of nodes at each level is going to double as we go further and further into the tree. So a complete binary tree is such a binary tree where every single node has a maximum number of children. And well, that basically means that the root should always have 2 children, right? Every single node, unless it's a leaf, should have exactly 2 children. So obviously on the first level, we'll say, well, 2 to the power of I minus 1, 1 minus 1 is going to give you 0, 2 to the power of 0 is 1. As you go further down into the tree, because every single time you branch out in 2 directions, the number of nodes is going to double. So we go from 1 node at level 1 to 2 nodes at level 2 to 4 nodes at level 3 to 8 nodes at level 4 to 16, 32, etc. So as the further down the tree you go, the higher the power of 2 becomes, and that power of 2 will basically tell you exactly how many nodes are stored on that level. Alright, so we finally get to the binary search tree. Binary search tree is a very simple and extremely efficient and smart data structure. It is once again a linked list that branches out, but what is very, very important is it's binary, so every single node is allowed to have a maximum of 2 children, so it can have 0 or 1 child or 2 children. Every single child is either on the left or the right hand side of the parent. And now we are actually going to finally add some relationship, which you can treat as hierarchical, I suppose. We will put the following rule onto how the values are stored inside of the binary search tree. We will say that all the children to the right-hand side of the parents must be larger, must store larger values than the values stored in the parents, and all the values on the left-hand side of the parents must store values that are actually less than the value stored at the parents. So if we store some n in that node, we will say that the entire right subtree of n, so all the nodes that you find on the right-hand side of n, must store values that are greater, and for the left subtree, the opposite is true. Only smaller than the element values can be stored in this left subtree. Great. And usually at this point, students ask me, but what if there are duplicates in the tree? What if I want to store 5 or 2 or something like that, some value twice in the tree? Well, you can always choose where the duplicates are going to go to. We can say, for example, that all the values in the left subtree are less than the elements, the parent element, and all the elements in the right subtree are greater or equal to the parent elements. However, for the purpose of this course, let us just assume that the values stored in the binary search tree are unique. So every single value is either greater or smaller than the elements. We will not have equality because duplicates are not allowed. For simplicity's sake, Let's say that is the rule of our binary search trees. Okay, so here is a bunch of examples of valid binary search trees. You can obviously store any values inside of your tree. It doesn't have to be integers, it can be objects, as long as the two objects are comparable to one another, as long as you can determine which one is bigger and which one is smaller, right? So this blue guy here on the left-hand side is the simplest one. We just store integers. The root is 5, so all the values in the left subtree must be smaller. As you can see, 3 and 1 are both smaller than 5. The same rule applies to the subtree, so if we only consider 3 and 1, 1 is stored to the left-hand side of 3 because it's smaller than 3 and that's where it belongs. On the other hand, the right subtree of 5 should store values that are actually larger than 5. And that is exactly what we are observing. 6, 7, and 9 are all larger than 5. Then if we independently consider just the right subtree, then right here the same rules apply. 7 is larger than 6, but it is smaller than 9. So the very same relationship of left is smaller, right is bigger applies to every single subtree inside of your entire binary search tree. This guy here, the red tree, only has a single value. This gray tree here stores characters, so the further you are in the alphabet, the larger you are. Z is larger than Y, therefore it's stored on the right-hand side. Here, A only has a right branch. C, D, and E all follow A alphabetically, so they are larger than A. C precedes D, it makes sense that it's on the left-hand side. E follows D, so it makes sense that it's on the right-hand side, etc. I hope you guys get the gist of it. Okay, so this is what we want to implement. Let's now look at how this is actually going to be implemented in Java. As always, the textbook actually provides some of the code. And as always, I'm not going to discuss specific Java syntax. So for example, if you're still not sure about extending the comparable interface, then refer to the following page of the textbook for a detailed explanation. But otherwise, remember, you are expected to figure out Java on your own. And hopefully you are getting to grips with it now that you have done your first practical and that you are busy with the second assignment. But anyway, let us look at a single node. So a single node of the binary search tree looks kind of similar to a single node in a linked list, right? It also stores some data of some arbitrary type T, which has to be comparable, right? We need to be able to determine who goes to the right and who goes to the left of any specific node. And then instead of storing a next pointer, we will store two pointers, a left pointer as well as a right pointer. So pictorially, you can imagine a node object to look as follows. It stores some elements and then it has the two pointers leading outwards, the left and the right pointer. And in the figures further, I will simply abbreviate it as follows. Okay, so let's talk about the algorithms now. How are we going to actually store data in a binary search tree? How are we going to delete data? Well, actually, in this particular lecture, we are not going to discuss insertion and deletion. Let us just assume that the tree already has data inside of it. What we are going to start with are the very simple algorithms. We will determine how to search a binary search tree for a particular element, and we are also going to discuss tree traversals. In other words, how do you actually visit every single element in the tree? How do you print out the contents of the tree to the screen, for example? So let's start with the search algorithm. I have already told you that the whole point of binary search trees is efficient search. So searching these guys must be more efficient than searching linked lists. Otherwise, why even bother? This is how the search is going to go. We are always going to start at the root. Just like with the linked list, you always start at the head. With the trees, the root is your only entry point, so that is where we are going to begin. You start at the root of the tree. If you're searching for a particular value, you take the value of the root and you compare it to the element that you are searching for. If you were searching for 5, so if the value is equal to the root, then good for you. You have already found the element you were looking for. However, if the element that you're looking for is not equal to the root, then determine whether the value that you're looking for is smaller or larger than the root. If the value that you're looking for is smaller than the root, in my case smaller than 5, then follow the left pointer. On the other hand, if the value is larger than 5, then follow the right pointer. And repeat the process recursively, right? So let's say I'm looking for 8. I started 5, 8 is larger than 5, therefore I'm going to go to the right hand side. I now compare 7 to 8, they are not equal, so I haven't found it yet. I'm going to go to the right hand side of 7. I compare 8 to 9, it's not equal. I try to go to the right, it's not equal, but 8 is actually less than 9, so I will try to go to the left hand side of 9. However, 9 doesn't have a left hand side, therefore I can only assume that 8 is not present in the tree. So I have never had to compare 8 to 3, 1 or 6. I have only compared it to the values here on the right branch of the tree. So I've only done 3 comparisons, even though I store 6 values in the tree. Here is the same thing in pseudocode. I did tell you that it's a recursive algorithm. By nature, it is recursive because you repeat the same thing, but because it's tail recursion, it's actually quite easy to implement it iteratively. So here's an iterative implementation. We start at the roots, and then we will say while you do not reach the end of the tree, keep comparing your elements to whoever is currently the current node that you're looking at. And based on the comparison, either return the elements if you found it, or either go left or go right. You never go both left and right. You always choose your path, and then hopefully your path takes you to the elements that you need. But this can very, very easily be rewritten recursively. Let's rewrite the search function in recursive terms. All right, here's the same algorithm rewritten recursively. The stopping condition is if the current element that you're looking at is null, then obviously you can only assume that element was not found. Second stopping condition, a termination criteria for recursion, is if you find an element, there is no need to iterate any further. So either if this pointer is null or if you found the element, if the pointer is null, just return the null. If you found the element, then return the element. Otherwise, do one of the following. If the element is less than the element stored in the current pointer, then go to the left of the current pointer. Otherwise, if it's larger, then go to the right of the current pointer. And either go left or go right until you meet one of the stopping criteria of this function. And I have already told you this is tail recursion because nothing really happens. There are no further operations happening inside of the search tree, as you can see, after the recursive call has been made. Okay, so this is all good and well. Hopefully this makes sense. I think the algorithm is pretty simple to understand. I did tell you that this algorithm is efficient. Question is, how efficient exactly is it? Well, I already told you that to determine asymptotic complexity, you need to count the number of operations performed. It turns out that the number of operations performed will to a very, very large extent be determined by the structure of the tree. Let's say you have the perfect binary tree, which is nice and balanced. In other words, almost every single node has 2 children, and the elements are nicely spread across this tree structure. If that is the case, if the tree is nicely filled and balanced, and we will come back to the question of how to balance the tree, then technically speaking, you might be able to eliminate half of the search space every single time you make the choice of whether to go left or to go right. So if I'm searching for 8, after performing a comparison between 5 and 8, I immediately decide that I will not consider the left branch. Therefore, I check away half of the search space. The entire left branch is not going to be considered for the search. I can only focus on the right branch. And then in the right branch as well, after comparison to 7, I immediately choose the side. And of course, the side that has not been chosen will not be considered. So you have the search space every single time. So what would then be the number of operations? How many times will I have to iterate? Well, the question is, how many times will I be able to divide my search space by 2, how deep is my tree, right? How big it is. And dealing with bigger complexity, you probably know what I'm driving at. If you are dividing your counter rather than decrementing it, we are looking at nonlinear speed up. So this will actually be expressed logarithmically, right? How many times can you divide something by 2? Well, you need to know what the power of 2 was that actually made the structure in the first place, right? How many levels it has. And to determine that, you need to simply take the logarithm of the total number of nodes inside of your tree. So the complexity is logarithmic, and as you hopefully remember, logarithmic complexity is very good. It is better than linear, much better than quadratic or exponential. So this definitely is a very, very significant speed up compared to ordinary linked lists. However, I did say in a perfect world. What if the world was not as perfect as I was hoping? Look at the tree on the slide. Is this even a tree? It looks more like a linked list, right? But technically, it actually meets the criteria of a binary search tree. Every single node has a maximum of 2 children. In this case, every single node has exactly 1 child. But that's fine, it is actually allowed. In the tree above, 3 also only has 1 child, and that doesn't make it less of a tree. So every single node here has only 1 single child, and that is a right child. Are the relationships preserved? Well, yes, D is larger than A, E follows D, F follows E, Z follows F alphabetically. So again, that relationship is also preserved. Basically, this tree is just one very, very long right branch with not a single left branch to be seen. Would this be efficient to search? Well, I guess if you're searching for something that's smaller than A, oh, but wait, A is actually the first letter in the alphabet, so there is nothing smaller than A. Essentially, searching a poorly structured tree like the one shown in the slide is as bad as searching a linked list. Complexity of the search in this case would be linear. So clearly, searching a binary search tree will really go different ways. Best case scenario, you get there in logarithmic time. Worst case scenario, you actually spend n iterations. Worst case scenario is linear time. In future lectures, we will actually discuss how to preserve the structure of the tree, even if you add and delete nodes, to make sure that logarithmic efficiency is maintained. But let's not get ahead of ourselves. Just keep in mind that binary search tree, if the tree is nicely balanced, is quite efficient, and we will later discuss algorithms that will allow us to preserve this efficiency. But generally, what we're aiming for here is obviously logarithmic. Okay, so hopefully you are now wrapping your mind around this. Hopefully you get more comfortable with the idea of the binary search tree. And we also have covered the search part of it. We now know how to search a tree. You start at the roots, you choose whether to take a left path or the right path by making comparisons to your current node until you reach the node that you're looking for or the leaf. Great, so that's one algorithm, search. The second algorithm that I want to discuss today is the traversal of a tree. And traversal is basically the act of accessing every single element of the tree. Traversal of the data structure is you visiting every single element for the purpose of perhaps creating a complete inventory of what is in your tree, or maybe printing it out in a nice format. Let's say I store student numbers in my tree, and perhaps the time comes when I'm interested in printing the class list. I'm not interested in just the right or the left branch. So the fact that it's nicely structured allows me to efficiently search for any individual student, but I still want the ability to print the contents of the entire data structure. And that is what we need the traversals algorithms for. Traversal algorithms are basically methods to systematically access every single node in the tree. It turns out that there are actually two main ways in which we can do this. So we are not interested in any random arbitrary order. In fact, we will discuss specifically two traversal types: breadth first traversal as well as depth first traversal. Let's do the breadth first traversal to begin with. So the idea of breadth first traversal is to visit the levels of the tree one by one. So we start at the top level at the root, we print the root, right? Then we want to go to the next level, print 3 and 7. Then we want to go to the next level, print 1, 6, and 9. So this kind of traversal makes sense if your tree indeed is a hierarchy, and the deeper in you go, the less important the nodes become, right? So perhaps the guy at the top is top of the queue, for example. So I start with that level. 3 and 7 will then be the next two guys on some imaginary queue. And the deeper in you go, the less important they become, right? Or maybe if I write a recursive algorithm, I can also do this in an upside down order. Start with the leaves, first print 1, 6, and 9, then print 3 and 7, and then print 5. But still, the idea of breadth first, breadth obviously stands for, the levels. We want to do this level by level. Any ideas on how to do this? Well, it turns out that the easiest way to implement a breadth first traversal is to actually make use of a secondary data structure. Specifically, we are going to use a queue. Here's pseudocode. Let's go through it line by line. So we are writing a non-recursive iterative method called breadth first, and the point here is we want to output all the nodes in the tree, and we want to do it in a level by level fashion. So we always start at the root. Remember, the root is basically the head of our linked list. We always begin at the root. Then we are going to create a secondary data structure called, in this case, a queue. Well, because it is a queue, it's going to be a queue of binary search tree nodes. What we then do is we say, okay, so as long as P, my current pointer, is not null, so if the tree is not empty in this case, obviously if root is null, you want to go here. But if the tree is not empty, then we're going to do the following. We take P, the current node, and we put it on the queue. We then say, all right, great, now while my queue is not empty, the queue, whoever is currently at the front of the queue, put it in my pointer P, then visit P. Visit in this case is just a placeholder method. Visit is the function that you should replace in the real world by whatever you actually want to do with this particular node. Maybe you want to print it to a file, maybe you want to print it to a screen, maybe you want to send it to some other function. So visit is not a part of my interface, it's just a placeholder. Replace visit by whatever you intend to do with every single node, because obviously you are traversing for a reason. You want to do everything with every single node. Whatever that something is, that is what the visit function is supposed to be doing. Great, and after I've visited my node, so printed it to the screen, for example, then I'm going to say, okay, great, I've processed this node. Now I will check, does this node have left children? If it has a left child, put that child on the queue. If it has a right child, put the right child on the queue as well. And that would end my while loop. And if I'm done with the children, I'll just go back and dequeue the next guy until the queue becomes empty. So essentially at every iteration, you dequeue whoever is currently in front, you visit that node, and then you enqueue his children before moving on to the next node on the queue. Let us see how this plays out in action. Here is a tree. I obviously want to visit it level by level. So this is how I want to print it. I want to start with 20, then print 10 and 30, then print 15 and 25, then do 23 and 27, and finally 26. I have put the entire code here in a block for reference, but let us actually see what happens to the queue and how things are processed along the way. So we begin by placing the roots on the queue. The queue currently has a single element, and that element is 20. What happens when we enter the while loop? Well, we immediately dequeue whoever is currently on the queue. We dequeue 20 and we print it. So out in this case is going to be the outputs. So my visit, obviously, I'll just print P to the screen, or do something like that. Great, 20 has been printed. What now? Before I go back to the top of the beginning of the while loop, I need to check if 20 has children. And it does, it has a 10 and a 30. So both of those are going to be put onto the queue. All right, that's the end of the code inside of the while loop, we go to the top of the loop, and what do? We dequeue the next guy. We dequeue 10. 10 gets visited, in other words, printed. So remember, this is how we want to print it: 20, 10, and 30. We managed to do 20 first, it was followed by 10, so far so good. It seems like we are succeeding at our level by level printout. Does 10 have children? It does not have a left child, but it does have a right child, 15. So 15 is added to the queue. All right, we go back to the top of while, and we dequeue whoever is next on the queue. That happens to be 30, because obviously 20 enqueued both of its children before anybody else had a chance. So let's see, are we successfully printing them in the right order? 20 followed by 10 followed by 30. 20, 10, and 30. Yes, we have successfully printed level 1. We have successfully printed level 2. Next up, we expect 15 and 25. All right, we've printed 30, but before we move on, we need to check if 30 has children. It does have a child, a left child, 25. So 25 is added to the queue. And the process continues. We're now once again going to dequeue whoever is in front. It's 15. 15 is printed. 15 does not have children, so it does not modify the queue. Next up, we dequeue 25. 25 is printed. And once again, look, we have managed to do 20, 10, 30, 15, and 25. So the first level, second level, and third level have successfully been printed. 25 has actually 2 children, 23 and 27. Both of those are going to be added to the queue. The process repeats. 23 is going to be printed next because it doesn't have children. We simply dequeue the next guy, who is 27, so 27 is printed. 27 does have a child, a left child specifically. So 26 is added to the queue. Finally, last iteration, 26 is printed. It doesn't have any children. So the next time we go to the while loop, we will see that the queue is indeed empty. So we have reached the end of the algorithm. We have printed all the values. And as you can see, we have managed to successfully print them level by level. 1, 2, 3, 4, and 5. They have appeared in exactly the order in which we wanted. Okay, so this is good. This works. Yes, we need to use an external data structure such as a queue, but it works very, very nicely in the queue, with the queue. However, what is the problem with this? Well, if indeed the levels represent the hierarchical relationships between the nodes, then this is indeed perfect. However, what if you wanted to print your values in ascending or maybe descending order? What if instead of printing them from level 1 to level 5, you wanted to start with the smallest value, which in this case is 10, and then print it all the way to the largest value, which in this case is 30, right? Does a tree structure allow you to write a simple traversal algorithm that actually manages to print values in a sorted order? It turns out that that is actually quite simple, and that is where depth-first traversals come in very, very handy. So the depth-first traversals, instead of focusing on the levels, rather focus on the branches. With depth first, we want to choose a branch, left or right. Once you've chosen your branch or subtree, you want to print that entire subtree before you go to the other subtree. So for example, I want to start, maybe in this case, I want to start with the left branch, print the entire left subtree. Only once I've printed the entire left subtree, only then will I go to the right subtree and then print all the values in the right subtree. So here depth rather than width is more important. That's why it's called depth first. You start on a node and then you go as deep as you can before you make a flip to the neighboring subtree. Question is, what are we going to output first as we go between the branches? Are we going to do first the left subtree, then the parent, then the right subtree? Because obviously in this case I have a left subtree and the right subtree, but also I have the parents that connects both of them, right? The root. So if I choose to do the left subtree and then the right subtree, or first the right subtree and then the left subtree, question is, what about the parents? Do I print him in between, after or before? How do I handle it? Well, actually, there are 3 types of traversals that you need to know: pre-order, in order, and post-order. In order is the most useful one because it actually prints your values in either ascending or descending order. But pre-order and post-order can also have a place, so let's discuss all of them. Let's start with pre-order first. This one is the most patriarchal of them all. We are going to start by printing the parent, and only after the parent has been printed, only then will you visit his left and right children. So parent is visited first, then you're going to do his children, and it's up to you whether you do left or right first. In my example, I'm assuming that left is always printed before the right for simplicity and consistency's sake. Okay, so we start with the root, which is 5. It's the parent, so he's printed. 5 has been printed. We now have to print the left child. However, the left child itself is an entire subtree. So to print the subtree, we need to apply the very same idea. We first print the parent, so 3. And then, now that we've printed the parent, the roots of the subtree, we can print the children of 3. 3 only has a single child, 1, and that child is printed. Okay, so depth first, we did the parent, then we did the entire left branch connected to the parent, and the very same rule applies to the subtree that is 3 and 1. Great, now we can move on to the right subtree. So we're going to go to 7. Again, this guy here is also a little binary search tree of his own, so we will apply the same rule. We will first print 7 because he's the parent of 6 as well as 9. Then 7 is going to be followed by his children. We'll first print the left child 6 and then the right child 9. Great. Pre-ordered traversal. How are we going to code this? It turns out that the code for depth-first traversals is the easiest to write if you write it recursively. And I think intuitively it makes sense. Trees themselves are defined recursively as data structures, and obviously every single subtree sort of has the same structure, right, as the biggest structure as well. So it makes sense that the very same logic will apply to every single branch and sub-branch of that sub-branch. So let's write a recursive algorithm. Here we go. It's very, very short and sweet. We are going to start a recursive algorithm on the root. Here is my recursive function. It essentially only has 3 lines of code. This is nice tail recursion. We say, okay, all right, if the node is not null, so obviously node be null is the stopping condition. If the node is not null, then visit it, in other words, print it or do something with it, call another function or do whatever you want with it. After you've visited your node, then just call the very same function on the left branch of this node, on the left pointer, as well as the right branch of this node. So we first visit the parent, print the parent, then we simply repeat this process for his entire left subtree and for his entire right subtree. Okay, but pre-order, as you can see, still outputs the values all jumbled up. We have 5 followed by 3 followed by 1, 7, 6, and 9. This is definitely not sorted. Please welcome in-order traversal. In-order is super useful because it does actually output values in a sorted manner of binary search trees. The idea here is quite simple. It's again going to be a recursive depth-first approach, but instead of printing the parent first, we will say, actually, because the children are smaller than the parents, if we first print everyone on the left-hand side, then the parent, then everyone on the right-hand side, then we'll have smallest, followed by a middle ground, followed by largest, which hopefully will end up with sorted order for us. So we start at the root. We do not print the root, instead we go to the left branch. This left subtree is going to repeat the same process. We are at the root of a subtree, the root is 3, but we don't just print 3, we go to the left child of 3. 1 doesn't have any more children, therefore we have reached the bottom. Since 1 doesn't have children, we are going to simply print 1 itself. Okay. We are done. No more deeper you can go from here, so we're going to backtrack to 3. Because 3 is the parent of 1, it has done its left-hand side, it will print itself. It will try to go to its own right branch, but because it doesn't have a right branch, it will now backtrack to 5. We are now at 5. 5 has successfully printed all of its left children, so it can now print itself. Because it has printed itself, it can now go and pass the control to the right-hand side. So we go to the right-hand side of 5. We follow the right pointer. we end up in the subtree. And again, the same logic applies. We are at 7, but we don't want to just print 7. We will say, hey 7, do you have a left child? If you do, let's print that first. 7 does have a left child, it is 6. 6 is printed, then 6 backtracks to 7, 7 prints itself, then it passes the control to 9, and finally 9 is printed. As you can see, this worked out quite well. We have values 1, 3, 5, 6, 7, 9, which is actually nice and sorted. We have not printed all the values in the tree in ascending order. How are we going to code this? Again, this has to be coded recursively because the structure of the tree just calls for it, and the code is actually going to be extremely similar to what you have seen on the previous slide. In fact, all you need to do is switch the order of the function calls around just a little. So the function is just as short. We start at the root. We will then say, as long as the current pointer is not null, first call the recursive function on the left branch, then print the parents, and then recursively call the very same function on the right branch. This is obviously non-tail recursion because we first do the left branch, then something important happens in between the two recursive function calls, right? We are actually going to output this middle right between the two function calls, and only then the right branch is followed. And if you wanted to print your values in descending order from largest to smallest, all you had to do was switch these two pointers around. If you first go to the right branch and then to the left branch, then you will end up with these values, but in reversed order. You will start at 9 and finish at 1. So that's quite useful, right? In just 3 lines of code right here, you can print the entire structure in a sorted way. It's surely quite convenient. And finally, the last traversal that you need to know is the post-order traversal. It's also depth first, but here we want to first print the children and then print the parents. So let's see how it's going to play out. We start at 5, we go to 3. We can't print 5 because we have committed to printing the children first. We can't print 3 because it might also have children, so 3 is going to go to its child. 1 doesn't have children, so it's going to print itself. It now backtracks to 3. Does 3 have any more children? No, it doesn't, so we can print 3. 3 backtracks to 5. Can 5 print itself? No. It still has children. It has to output all of its children before it presents itself. So 5 is going to pass control to 7. 7 is also a parent. It has a 6 and a 9 as its children. So it will first print 6, then print 9, and only then we will be able to print 7. Then we're going to backtrack to 5 and finally print it after all the children of 5 have been printed. Again, implementation is extremely similar to the previous 2 slides. All we need to do to achieve this other type of traversal is shuffle the order in which the function calls are done. We're now first going to do a recursive call on the left branch, then we're going to do a recursive call on the right branch, and only after both of these branches have been visited and printed, only then are we going to finally visit the parent itself. Alright, so that was binary search trees. Just to summarize what we've learned today, binary search tree is a linked data structure where every single parent can have a maximum of 2 children. Every single child is either a left or a right child. To make a binary tree, a binary search tree, you also need to add a relationship between the values. All the values in the left subtree must be smaller than the parent, than the root, and all the values in the right subtree must be larger than the root. Obviously, every subtree of a tree is also a binary search tree. Binary search trees that are balanced are going to be efficiently searchable, and the efficiency of the search is logarithmic. We have covered traversals, breadth first and depth first. With breadth first, we go through the levels. With depth first, we go as deep into a branch as possible before we move on to the next branch. We've also done in-order, post-order, and pre-order traversals. Make sure that you're comfortable with all of them. Alright, so this is all I have for today. Thank you very much. In the next lecture, we are going to discuss more traversals of binary search trees, and we are going to see how binary search trees can be traversed without using recursion or a stack. Yeah, thanks a lot. Stay tuned.